In this video, we're going to be looking at what's called the Carnot heat engine, which is essentially a two-temperature heat engine, as we've shown here in our typical black box representation. And what makes it a Carnot heat engine is that it is the ideal heat engine that has the best possible thermal efficiency. So I've drawn our control volume here, and we're going to do a first law analysis over this control volume. So coming in, we've got Q dot H, and we have leaving Q dot C, and leaving also is the work, the net work of the cycle. So that'd be your turbine work minus your pump work, and that's going to be equal to the rate of energy change within the system, which of course, if we're operating our power cycle at steady state, goes to zero. And so then from this expression, we can solve for Q dot C, which is the waste heat, and that's going to be equal to the heat input to the cycle minus the work output. And we'll call that one equation 1. Next we move on to the second law, which in this case will be the entropy that's generated within the control volume, and that will be equal to the rate of change of entropy inside the control volume minus the entropy transfer associated with heat transfer, so that's going to be Q dot H divided by TH minus Q dot C over TC. So this is our closed system second law expression, and of course it's steady state, and so we can then solve this expression for QC. So Q dot C will be Q dot H over TH. That'll be multiplied by TC, because that's coming from the final term in the equation above, and then we'll have plus TC times the rate of entropy generation, which is S gen dot. So we'll call this equation 2, and basically now we have two expressions for the heat that's going into the sink, the cold temperature sink, and we can set those two equal to one another to eliminate that. So if we take the right-hand side of equation 1, we've got our Q dot H minus W dot. That comes from the first law, and we'll set that equal to the expression that comes from the second law, so Q dot H over TH multiplied by TC plus TC times S gen dot, the rate of entropy generation. So ultimately, the purpose of the power cycle is to produce work, so we're going to solve for that. And so if we solve for the amount of work that's produced, we will pull out the heat input, and that will be multiplied by 1 minus Tc over Th. So the first term here is coming from this one, and then when we move this to the other side is where this factor Tc over Th comes from. And then there's just one more term, and that will be minus Tc times S gen dot. So now we'll just focus in specifically on this term. So first of all, we can say that this is always positive. And that's because the temperature Tc is of course an absolute temperature, and as we know from the increase of entropy principle, Sgen is also always positive. What we can also conclude, since this is always positive and we've got a negative sign in front of it, that the generation of entropy is always going to reduce the work output. So on the left-hand side is our work output. This is always taking away from that work output. So what we can say from this is that if we want to maximize the work output, we want this term to be as small as possible. We know that Sgen has to be greater than or equal to 0, so the best case is where Sgen equals 0. So to summarize, if we want to maximize the work output, we must minimize Sgen, and the best case that we can have is where Sgen is equal to 0. Now, if we take the resulting equation for the work or power output and we set Sgen equal to 0, then this is going to be our expression. And this represents the best possible work output that you can get for a given heat input and a given temperature for your source and sink. So now we go back and we substitute this into our thermal efficiency. So eta T, again, it's the desired effect or the output of the system, which is W dot, divided by whatever is the cost to us, which in this case is the energy we put in, Q dot H, and we substitute in the expression here from the instance where the entropy generation rate is 0, and of course the QHs will cancel one another, and so we can call this eta T, and we're going to give it the superscript C, which stands for the Carnot, and then that's going to be 1 minus Tc over Th. Okay, so this quantity is our Carnot efficiency, and what that represents is it's the maximum possible thermal efficiency that we can obtain in the ideal case where the entropy generation is 0 for a given temperature of both the source and the sink. So the Carnot efficiency depends on what the temperatures are of the source and sink, but given those temperatures, this tells us what is the best possible thermal efficiency